In the past half-century, quiet discoveries have slipped into the light and gently unfolded the universe in ways no one expected. Thousands of worlds beyond the sun emerged. The unseen weight of dark matter showed its subtle pull. Dark energy revealed a universe speeding outward and at the heart of our own galaxy. A black hole millions of times heavier than the sun reshaped everything we thought we knew. Tonight, in this calm decoding of the cosmos, you drift slowly through that transformation. From Voyager 1 brushing past the border of the solar system, to Hubble unveiling galaxies in a patch of sky once believed empty, to JWST revealing the earliest structures ever formed. Let your breath settle, let your shoulders soften, and follow each quiet measurement as it gently redraws your sense of reality. And now the first turning in the story arrives. Part 1. How did just 50 years overturn our entire picture of the universe? NASA once said, our understanding of the universe has turned upside down. It wasn't an overstatement. Within a single generation, the worldview that felt so steady at the end of the 20th century dissolved quietly, replaced piece by piece with discoveries no scientists in the 1970s could have foreseen. And tonight, in this peaceful corner of the cosmos, you move through that shift slowly. Each change came not from speculation, but from measurements, readings collected by telescopes, probes, satellites, and detectors capturing the universe in kilometers, Kelvin, seconds, and electron volts. Over 5 patient decades, those numbers transformed everything. When the 1970s closed, astronomy textbooks still pictured a solitary kind of solar system. No world beyond our own had been verified. The center of the Milky Way was thought to be a gentle region of stars. Galaxies were assumed to turn at speeds explained neatly by the gravity of visible matter, and the universe's expansion, first noticed by Edwin Hubble in 1929, was expected to slow as gravity pulled everything inward. But the next 50 years, from 1975 to now, quietly swept those assumptions away. The revelations didn't arrive all at once. They appeared in soft, steady steps, like faint pulses from distant space, forming a pattern only when seen together. The shift began with planets in 1992. Radio astronomers Alexander Volshan and Wolf Shan and Dale Frail found the first confirmed exoplanets, orbiting a pulsar named PSRB 1257+12, an unlikely cradle for worlds, circling a neutron star spinning dozens of times each second. Yet the planets revealed themselves in tiny timing variations measured in milliseconds. Then, in 1995, Michel Mayor and Didier Queloz announced a planet around a sun-like star. 51 Pegasi Bs sweeping around its star every 4 days at a distance of only 7 million kilometers. Its tight orbit broke every planet formation expectation of that era, but the measurements were unmistakable. A new class of worlds existed. NASA later called this moment the true beginning of modern exoplanet science. From there, thousands of planets surfaced: hot Jupiters, super-Earths, mini-Neptunes, water worlds, scorched iron spheres, tidally locked systems with permanent day on one side and endless night on the other. One discovery after another erased the tidy blueprint once assumed universal. Astronomers began saying, there are more planets than stars in the Milky Way. That single realization lifted the idea of a typical solar system from our hands. It meant the cosmos was overflowing with possibilities, and our home was just one arrangement, among countless others. The next revelation came from the Milky Way's core. In the early 1990s, Andrea Ghez and her team at UCLA traced the paths of stars near the galaxy's center using infrared telescopes. Stars like S2 and S29 moved at thousands of kilometers per second, looping in precise ellipses around something unseen. Year after year, the data accumulated until the answer could no longer be avoided. At the heart of the Milky Way lay a supermassive black hole, about 4 million times the Sun's mass. Ghez later reflected, "We were watching the fabric of space stretch in real time." By the late 1990s, astronomers realized nearly every major galaxy carried such a giant, not rare outliers, but central engines guiding galactic evolution. But an even deeper shift was waiting, hidden in the way galaxies spin. In the 1970s, Vera Rubin studied how stars and spiral galaxies moved. Newtonian physics suggested that stars near a galaxy's edge should drift more slowly than those close to the center. But Rubin's careful observations told a different story. The stars moved far too quickly, faster than the visible mass could possibly hold. She once remarked, "What you see in a spiral galaxy is not what you get." This became the first strong clue for dark matter, a form of mass that doesn't shine or absorb light, yet outweighs ordinary matter by roughly 5 to 1. Without it, galaxies would unravel. With it, the structure of the universe finally fit together. Still, it remained invisible. Scientists could trace it only through gravity, through velocities, measured in kilometers per second, and masses inferred from vast surveys, stretching across megaparsecs. Year after year, detectors searched for interactions from particles like WIMPs, ixions, or even primordial black holes. But no definitive signal appeared. That silence deepened the mystery, transforming dark matter from a simple explanation into one of cosmology's central puzzles. Yet the most astonishing discovery of all involved not planets, not galaxies, not even matter, but the universe itself. In 1998, two independent groups studying type Ia supernova, the HISE Supernova Search Team and the Supernova Cosmology Project, MEASURED, how fast distant galaxies were drifting away. They expected to see the expansion slowing under gravity. Instead, the data revealed acceleration. The universe wasn't easing to a stop. It was speeding up. Adam Rees later said, "It was the moment we learned the universe had a force we never imagined." That force, Sue named dark energy, now accounts for about 70% of the total energy in the cosmos. It revived Einstein's cosmological constant, an idea he once dismissed as his greatest mistake. But the numbers aligned. A constant energy density permeating space itself could drive accelerated expansion. This meant the universe's future was no longer a gentle gravitational settling, but a long, steady drift into growing separation. Each of these discoveries, exoplanets, galactic centers, dark matter, dark energy, built quietly on the others. None relied on speculation. All arose from measurements gathered by instruments, NASA, ESA, and observatories across the world. Constructed with extraordinary precision, Hubble observed galaxies billions of light years away, piecing together early cosmic history from faint, red-shifted photons. Voyager 1 crossed into interstellar space, its plasma wave detector sensing subtle changes in density as it passed beyond the helium. The Planck satellite mapped the cosmic microwave background at a resolution of 5 arc minutes, revealing temperature differences of just tens of microkelvin. Every measurement added a new layer. Every layer pushed old expectations aside. By the early 2020s, the transformation was complete. The universe described today is not the universe described in 1975. It is larger, stranger, expanding faster, and filled with unseen components. It holds more planets than stars, more dark matter than atoms, and more dark energy than everything else combined. 50 years carried us from a cosmos guided by simple gravity to one shaped by invisible mass and a repulsive energy filling every cubic meter of space. And that shift returns scientists to NASA's quiet conclusion. Our entire understanding of the universe has turned upside down. As you follow these steps, a new realization begins to form. Soft but persistent, rising like a distant signal. Just beginning to reach you. If 50 years could remake our entire picture of the cosmos, what happens when we measure the very edge of the solar system itself? That path leads directly into part 2. Why did Voyager 1 become the symbol of humanity's leap into a new cosmic age? The most distant object humanity has ever touched began its journey at a time when we didn't even know if planets existed beyond the Sun. To understand why, Voyager 1 became a marker of a new era. You drift back to 1977, the year we sent a spacecraft into a universe we barely understood. A year that quietly divided astronomy into before Voyager and after Voyager. When Voyager 1 lifted from Cape Canaveral on September 5, 1977, NASA still worked within assumptions inherited from mid-20th century astronomy. No exoplanet had been confirmed. The galactic center seemed ordinary. Dark matter was only an early idea supported by tentative rotation curves. Dark energy had not yet entered the language of cosmology and the boundary of the solar system. The true frontier was unknown. Voyager launched into that uncertainty. Its instruments were crafted not for interstellar space, but for brief encounters with Jupiter and Saturn. Yet the spacecraft soon surpassed every expectation, revealing structures and processes that reshaped our understanding of planets. Magnetic fields, atmospheres, radiation belts, and the transition between the Sun and the galaxy. Voyager became the symbol of a new age for a simple reason. It carried us from a universe of assumptions to a universe of measurements. Through signals sent from more than 20 billion kilometers away, it replaced speculation with observation. Its discoveries began almost immediately. When Voyager 1 passed Jupiter in March 1979, it captured eruptions on Io, plumes of sulfur and oxygen rising hundreds of kilometers high. Until then, active volcanism beyond Earth had never been witnessed. Scientists had expected stillness and cold. Instead, Voyager revealed one of the most geologically active worlds in the solar system. At Ganymede, it detected a magnetic field, the first confirmed around a moon. And on Europa, faint surface fractures hinted at a subsurface ocean tens of kilometers deep. A possibility NASA would later describe as one of the most promising places to search for life in our solar neighborhood. Then came Saturn. Voyager 1's 1980 flyby showed that Titan, Saturn's largest moon, held a thick nitrogen atmosphere even denser than Earth's, with methane clouds drifting above a surface hidden beneath haze, evidence of rich organic chemistry. Each of these findings chipped away at the older picture of a simple, predictable solar system. Voyager revealed instead a realm alive with chemistry, internal heat, magnetic structures, an active geology, a miniature reflection of the universe's broader complexity. But the deepest shift came long after the planetary encounters. For decades, Voyager continued its outward path, past the orbits of Uranus and Neptune, beyond dwarf planets, into the thinning reach of the Sun's influence. By 2010, it began approaching the heliopause. At the far edge of the Sun's reach, the solar wind, a steady outflow of charged particles racing outward at hundreds of kilometers per second, finally begins to slow. Beyond that point, it yields to the interstellar medium, the vast sea of particles between the stars. For decades, scientists had only broad guesses about where this transition might lie. Some estimated 80 astronomical units, others suggested 200. No mission had ever touched it. Then, on August 25, 2012, at roughly 121 astronomical units from home, Voyager 1 slipped into interstellar space. The confirmation came not from a photograph, but from the plasma wave instrument, which sensed a sharp rise in particle density around the spacecraft. NASA summarized the moment with quiet clarity. Voyager 1 had entered interstellar space. Humanity had sent a machine beyond the heliosphere, the bubble our sun presses into the galaxy. This crossing signaled more than technological success. It marked the instant human exploration stepped fully outside the solar system. To understand why that moment carries such weight, you return to what the world knew when Voyager launched. No confirmed exoplanets, no evidence of supermassive black holes, no hint of dark energy, no microwave background maps with micro-Kelvin precision, no gravitational wave DETECTIONS. By the time Voyager passed the heliopause, each of those discoveries had transformed our view of reality. Its 50-year journey had become a quiet timeline of cosmology's greatest leaps. Think of exoplanets. When Voyager left in 1977, none were known. Today, NASA's catalogue holds more than 5,000 confirmed worlds, and the Kepler and TESS missions suggest that planets accompany nearly every star. Voyager's lifespan spans the shift from no known worlds to a galaxy overflowing with them. Consider black holes. In the 1970s, the idea of giant black holes at galactic centers was debated, but unproven. Decades later, Andrea Ghez and Reinhard Genzel measured stars whipping around the heart of the Milky Way at more than 7,000 kilometers per second. Their work revealed a Formian solar mass black hole at the galaxy's core. Voyager's voyage overlaps with that revelation, the discovery that our galaxy is far more dynamic than once imagined. And then dark matter. In 1977, Vera Rubin's rotation measurements were just beginning to hint at missing mass. 50 years later, dark matter is estimated to compose about 85% of all matter. The Planck satellite confirmed this through precise mapping of the cosmic microwave background. Dark energy followed a similar path. Completely unknown at the time of Voyager's launch, it is now believed to account for roughly 70% of the universe's total energy. Adam Rees described its discovery as the moment we realized the cosmos contained a force we never expected. Voyager's outward journey echoes this expansion of knowledge. Its steady motion through the solar system became a gentle metaphor for the widening boundaries of human understanding. But there is a detail often forgotten. Voyager did not leave the solar system empty-handed. It carried a message. The Golden Record, assembled by Carl Sagan and a small committee, holds sounds from Earth, greetings in dozens of languages, and images encoded in analog form. Sagan once reflected that the record would be encountered only if advanced spacefaring civilizations arose somewhere in the interstellar depths. It is both a scientific artifact and a quiet measurement, a snapshot of Earth, carried by a craft moving more than 17 kilometers per second relative to the Sun. Voyager's most famous image arrived earlier still, the pale blue dot taken in 1990, at Sagan's suggestion, shows Earth as a tiny point suspended in a shaft of scattered sunlight. NASA called it one of the most powerful reminders of our planet's fragility. Its significance, though, is grounded in physics. It demonstrates the geometry between the spacecraft and the Sun at 6 billion kilometers, the behavior of scattered light inside the camera, and the sensitivity required to detect a planet from that distance. After that picture, the cameras were turned off to preserve power. Across all these years, Voyager's instruments continued sending data. The cosmic ray subsystem recorded streams of charged particles. The magnetometer traced shifting magnetic fields. The plasma wave detector measured particle densities. The low-energy charged particle instrument monitored the solar wind's fading strength. Each reading revealed something unexpected. Particle densities rose sharply near the heliopause. The magnetic field direction changed in sudden, uneven steps. Galactic cosmic rays increased once the probe entered interstellar space. These measurements provided the first direct look at the region that surrounds the solar system, a frontier that had existed only in theory. Voyager became the first messenger to capture physical data from that boundary. This is why it represents the beginning of a new cosmic era. It marks the threshold where our tools began probing not just planets, but the structure of the galaxy itself. Interstellar space is no longer imagined. It is measured. Behind this achievement lies a quiet story of endurance. Voyager's systems were engineered for a 5-year mission. The plutonium power source was expected to fade steadily. Yet through meticulous power management, shutting down heaters, rotating instruments, reallocating energy, the spacecraft remains functional nearly half a century later, in 2023. Its plasma wave instruments still return data from more than 24 billion kilometers away. Commands now take over 22 hours to reach the probe and another 22 hours to come back. Yet the connection holds. The Deep Space Network continues listening. Its 34-meter and 70-meter antennas catching the faint whisper of a spacecraft still moving outward, still sending home its steady stream of measurements. Instruments are attuned with quiet precision, adjusted gently to match the fading power. Voyager endures because generations of engineers, scientists, and operators shaped every system so it could be persuaded to last just a little longer. And that devotion reflects the scientific path of the last 50 years. Tonight, you meet Voyager, not only as a spacecraft, but as a timeline, a vessel tracing how our picture of the cosmos changed, while one probe drifted steadily outward. It launched into a universe with no known exoplanets. It now moves through a universe shaped by dark matter, pushed by dark energy, and filled with planets circling nearly every star. And as you neared the next part of this journey, a quiet question rises forming naturally from Voyager's long outward glide. If one spacecraft expanded our idea of distance and frontier, what happens when you learn that the planets it left behind are not rare at all? That thought carries you softly into Part 3. Why did the discovery of thousands of exoplanets undo the old map of the cosmos? Astronomers once believed our solar system was ordinary, but that certainty dissolved the moment the first world was found around another star. From a universe with none, you now stand in a galaxy where NASA says plainly, there are more planets than stars. And that shift from 0 to thousands and woven the entire planetary blueprint scientists trusted in the 1970s. The story opens in an era when astronomy textbooks still pictured the solar system as a calm, orderly family of worlds. The sun at the center, for rocky planets warmed by its light, for giants farther out, wide orbits traced like smooth rings. Beyond them, darkness. But by the late 20th century, telescopes grew sensitive enough to detect faint stellar motions. Tiny shifts measured in meters per second movements, caused by the pull of orbiting planets. Those subtle changes in starlight offered the first hints that the universe held far more worlds than the one you knew. The breakthrough arrived in 1992, when Alexander Volshan and Dale Frail found planets around PSR B1257 plus 12. A pulsar spinning dozens of times each second. These planets revealed themselves through delicate timing variations, slight irregularities in radio pulses from the neutron star. No one imagined the first exoplanets would circle such an extreme object. Then in 1995, Michel Mayor and Didier Queloz announced a world unlike anything in our system, 51 Pegasi b, completing an orbit in just 4 days, only 7 million kilometers from its star. A giant planet pressed close to its sun, a hot Jupiter. NASA later said, this discovery marked the birth of modern exoplanet science. The surprise was not the world itself, but what it implied. Every formation model predicted giants should arise far from their stars. Yet 51 Pegasi b clung tightly to its own. That contradiction forced astronomers to revisit the physics of disks, migration, and orbital evolution. And from that moment onward, discoveries multiplied. Kepler, launched in 2009, watched a single patch of sky, waiting for tiny dips in starlight caused by planets passing in front of their stars. These dips were incredibly small, sometimes 1 part in 10,000. But Kepler's steady instruments could sense even those faint signatures. Across 9 years, Kepler revealed thousands of worlds. Planets larger than Earth, but smaller than Neptune. Giants skimming close to their suns. Small, rocky planets racing in tight orbits. Worlds resting in habitable zones where liquid water might exist. NASA wrote, Kepler has shown that planets are common, not rare. This realization transformed astronomy. Instead of viewing the solar system as a standard pattern, scientists began to see it as one arrangement among countless others. TESS Transiting Exoplanet Survey satellite extended the search across nearly the whole sky. It observed thousands of bright stars, discovering planets close enough for JWST to examine. And JWST, with its infrared precision, began detecting chemical imprints in alien atmospheres. On planets like WAS 39b, it found carbon dioxide, water, vapor, and sodium. On others, it detected signs of silicate clouds. These measurements came from watching how starlight passed through an atmosphere, revealing absorption lines linked to specific molecules. Even the smallest decrease at certain wavelengths could reveal a planet's chemistry. Through this method, astronomers classify worlds by measurable traits: temperature, composition, density, and orbital dynamics, not speculation. Each discovery carried its own quiet story. Kepler's first Earth-sized worlds appeared only after scientists examined hundreds of faint dips across years of data. These dips nearly blended into noise fluctuations in sunlight, shifts in instrument temperature, cosmic rays striking sensors. Teams worked for months to confirm each signal. When Kepler 452b was announced, NASA called it the closest yet to Earth in size and temperature. Scientists had analyzed changes in brightness measured in parts per million, variations lasting only hours, to confirm the transit was real. Behind it lay months of data correction, atmospheric filtering, and comparisons across detectors. Other systems, like TRAPPIST-1 with its 7 rocky planets, required a global network of observatories to track their overlapping transits. Their gravitational, choreographed orbit linked mathematically to the next was revealed through repeated timing variations recorded over hundreds of cycles. Those patterns confirmed something extraordinary: multiple worlds inside of stars. Habitable zone. ESA later wrote, TRAPPIST-1 remains one of the most intriguing planetary systems discovered. As these findings accumulated, the old cosmic model faded away. Astronomers once believed planetary systems were rare. Giant planets formed only in distant regions. Habitable zones were narrow. Rocky worlds were uncommon. Earth-like planets might not exist elsewhere. Now, the evidence points in the opposite direction. Planets form easily. Orbital designs vary widely. Migration is frequent. Rocky worlds appear abundant. And NASA states simply, Earth-sized planets in habitable zones are likely common. This shift removes the sense of uniqueness. The solar system is not a blueprint, just one example among billions. The Milky Way likely holds about 1 planet per star, meaning hundreds of billions of worlds scattered through a galaxy only 30 kiloparsecs wide. The consequences extend far beyond astronomy. If planets are common, chemistry is common. If chemistry is common, complex molecules are common. If complex molecules are common, the potential for habitability is not rare. This does not promise life, but it dissolves the idea that Earth occupies a special category. The refinement deepens through atmospheric study. JWST's spectroscopic tools allow scientists to infer temperatures, cloud layers, and heavy elements such as oxygen, carbon, and sulfur. This offers a new way to assess habitability by studying how an atmosphere holds heat, reflects light, and responds to stellar radiation. One example is the detection of sodium and potassium lines in the atmosphere of HD 209,458b. These features revealed atmospheric circulation and temperature contrasts, signs of strong winds driven by intense stellar light. Such clues help scientists understand how atmospheres evolve under different conditions. Another is the measurement of thermal phase curves, small shifts in infrared brightness as a planet orbits. These patterns show how well a planet redistributes heat, revealing winds, clouds, or temperature differences between day and night. Behind every measurement lies a human story. Long nights in control rooms, teams correcting detector drift, engineers refining sensors to detect signals measured in microelectron volts. Scientists often say the process changes them. Astronomer Jeff Marcy once remarked, "Each new world we find forces us to reconsider the rules." With every discovery, the old structure gave way. And yet the most meaningful shift is not numerical, it is structural. For the first time, planetary systems can be compared statistically. By analyzing sizes, densities, orbital periods, and star types, patterns appear. Planets around small stars are common. Compact systems with many close-in worlds are frequent. Gas giants often form far out before drifting inward. A star's heavy element content correlates with the likelihood of giants. These patterns were invisible before. Now planetary science rests on measurable quantities, orbital speeds in kilometers per second, radii derived from starlight dips, masses from velocity shifts, atmospheric signatures revealed through spectroscopy, and through these numbers, a new image forms quietly behind everything, one that suggests the Milky Way is far more textured and populated than once believed. As this understanding settles, a new curiosity rises gently at the edge of the journey. If planets are this abundant, then what did Hubble reveal when it stared into apparent emptiness? That quiet thought carries you into part 4. Why did the Hubble deep field show that the universe is neither special nor rare? Astronomers once believed there were regions of sky so empty that nothing waited behind them. But in 1995, that idea collapsed when Hubble aimed at a patch of darkness and uncovered galaxies everywhere. A region smaller than a grain of sand held at arm's length contained thousands of distant systems, each a structure filled with billions of stars. That one observation erased the idea of cosmic rarity, revealing with absolute clarity that the universe repeats itself across unimaginable distances. The story began quietly in December 1995, when the Hubble Space Telescope was pointed toward a small area near the Big Dipper. The selected patch looked empty. No bright stars, no nebulae, nothing ground-based telescopes could separate from noise. Some worried the time would be wasted, but others believed that staring into nothing might reveal what lay behind the glow of nearer objects. Over 10 days, Hubble gathered photons from that darkness. Each exposure captured light that had been traveling for billions of years. Arriving from times shortly after galaxies first formed, when the data were combined, the empty region transformed. Every point of darkness became structure. Every faint speck resolved into a galaxy's spirals, ellipticals, star-forming clumps, shapes stretched by interactions. NASA summarized the results simply: the universe is far more crowded than we imagined. In a patch covering just 1-20-4-millionth of the sky, Hubble counted nearly 3,000 galaxies. If that density is typical, the observable universe contains well over 1 trillion galaxies. This realization carried immediate meaning. First, it demonstrated that galaxy distribution on the largest scales is remarkably uniform. Every direction holds structure. Every angle reveals the same cosmic fabric. The idea that our galaxy occupies a special place faded at once. Second, it strengthened the principle that large-scale uniformity, what cosmologists call isotropy, is a built-in property of the cosmos. When NASA compared the deep field to maps of the cosmic microwave background from COBE and WMAP, the same message appeared again. The universe looks the same across vast distances. But the deepest part of this discovery rests not in the data itself, but in the quiet effort that made it possible. The Hubble Deep Field depended on holding the telescope perfectly steady for long stretches of time. Engineers had to correct for Earth's motion, the gentle expansion of Hubble's structure with temperature, and tiny vibrations from the spacecraft's own machinery. The accuracy required was finer than a strand of hair seen from kilometers away. Each exposure used different filters, allowing scientists to separate galaxies by their colors, a method that hints at their ages and distances. The reddest systems often mark the earliest eras, their light stretched by cosmic expansion into longer wavelengths. Some formed when the universe was only a fraction of its present age. This was not assumption, it was measurement. Spectroscopic follow-ups from NASA, ESA, and observatories on the ground confirmed the distances. Redshift values revealed exactly how far those photons had traveled. And behind every redshift lay a story. Within the deep field were galaxies forging stars at rapid rates, glowing in ultraviolet light from massive young suns burning through hydrogen. Others showed the signatures of mergers, their shapes pulled and twisted by tidal forces. Some appeared faint and compact, likely early galaxies gathering their first generations of stars. Together, they showed the universe not as a still portrait, but as a landscape evolving across cosmic time. What made the result even more striking was its consistency. When Hubble repeated the experiment in 2004 with the ultra-deep field again pointing at a region that seemed empty, the outcome was unchanged. Galaxies everywhere, astronomers later wrote. Every deeper look reveals more galaxies, not fewer. Then, with the extreme deep field, researchers combined 10 years of exposures. The image captured galaxies only a few thousand light-years, wide, tiny structures compared to the vast spirals of today. These small galaxies represent the universe's earliest architectural steps. Their uniform presence supported a central idea in cosmology. The universe is homogeneous on large scales. This does not mean everything is identical. It means that when distances reach hundreds of millions of light-years, the distribution of matter becomes roughly even. Yet this discovery raised a quiet, puzzling question. If the universe is uniform across tens of billions of light-years, how did such smoothness arise? According to the Standard Model, regions separated by enormous distances should never have interacted early on. Light could not have crossed between them. And yet the temperature of the cosmic microwave background measured by COBE, WMAP, and Planck remains remarkably consistent. Planck scientists described it as a uniformity that demands explanation. This is the horizon problem. How can places that never touched share the same physical state? The deep field did not solve the puzzle, but it made it visible. The smoothness of the background radiation echoed the smoothness of the galaxies uncovered. In Hubble's view of darkness, cosmologists turned to inflation to explain how the early universe might have evened itself out before expanding. Asterisk. The deep field also added clarity to the structure of the cosmos. The universe forms a web of filaments and voids threads traced by galaxies across vast distances. Although the deep field spreads galaxies uniformly across the image, three-dimensional maps like those from the Sloan Digital Sky Survey reveal walls, clusters, and long strands of matter. These stretch for hundreds of millions of light-years. Yet at larger scales, the distribution returns to uniformity. Asterisk. Hubble's images hinted at this framework by showing galaxies of different ages. Older, redder ones traced the skeleton of the cosmic web. Younger, bluer ones filled the spaces where gas had recently condensed. More recently, JWST pushed this view further, detecting galaxies at even greater redshift, some above 10, meaning their light was emitted when the universe was under 500 million years old. These early systems challenge models of how quickly stars and galaxies form. NASA noted JWST has revealed galaxies earlier and brighter than expected. With this evidence, cosmologists refine simulations of galaxy formation, adjusting details of dark matter, gas physics, and stellar feedback. These models show how tiny fluctuations in ancient density fields grew into today's cosmic structure. Every detail matters: star formation rates, cooling times, supernova feedback, the pull of dark matter halos. The deep field serves as the observational anchor linking simulation to reality. Without it, models would drift without grounding. Behind the deep field is also a story of risk. At the time, some argued that devoting so much observing time to an empty region was unwise. Others believed that seeing the early universe required looking where nothing nearby interfered. That debate reflected a broader tension between the known and the unexplored. When the first image appeared, many were stunned. The sheer number of faint, distant galaxies showed how much of cosmic history remained hidden. Carl Sagan later reflected on deep views of space by saying, "We are a way for the cosmos to look back upon itself." In the deep field, the universe looked back across billions of years. The image changed not just the map of the cosmos, but the expectations behind it. After 1995, astronomers understood that every dark corner of the sky hid galaxies far too faint for earlier telescopes to see. No region was empty. Every region was full. The discovery also shaped instrument design. Engineers building JWST and AIR. The Roman Space Telescope calibrated detectors to capture extremely faint light. They improved optical stability, infrared sensitivity, and pointing precision. These advancements came directly from the lessons of the deep field. One image had shown what was possible by reaching deeper now. When astronomers examine JWST's deep views, where each tiny point contains galaxies at different stages of growth, they see structures consistent with, yet stretching beyond, Hubble's earliest glimpses. The Euclid mission adds another piece by mapping dark matter through gravitational lensing, revealing how mass bends light and sculpts cosmic architecture. These lensing signs often appear in deep fields where background galaxies are stretched by foreground structures. Every measurement reinforces the idea that the universe behaves consistently across vast distances. And as tonight's quiet journey draws nearer to its next moment, a gentle question rises at the edge of this wide, repeating cosmos. If the universe mirrors itself everywhere you look, then what hidden structure lies at the heart of your own galaxy? That soft curiosity carries you into part 5. Why did the 1998 discovery of a supermassive black hole in the Milky Way change everything? Astronomers once believed the galactic center was simply a crowded cluster of stars. But in 1998, precise measurements revealed something impossible. Stars near the core were racing around an unseen object at thousands of kilometers per second. Their swift motion pointed to only one conclusion: a mass 4 million times heavier than the Sun, compressed into a region smaller than Mercury's orbit. That moment revealed a supermassive black hole anchoring our galaxy and quietly reshaped our understanding of how galaxies form, grow, and evolve. The road to that discovery stretched back decades. For years, astronomers suspected something unusual lay at the center of the Milky Way. Radio observations detected a powerful source near Sagittarius, compact region later called Sagittarius A*. But seeing the galactic center was famously difficult. Dust clouds blocked visible light, scattering and absorbing photons before they reached Earth's telescopes. To peer through that dust, astronomers needed infrared instruments capable of catching heat like light that slips through dense regions. In the early 1990s, teams at the Keck Observatory in Hawaii and the European Southern Observatory developed infrared cameras with unprecedented clarity. Among the scientists leading this work was Andrea Ghez of UCLA. Her team focused on a cluster of stars orbiting extremely close to Sagittarius A*. These stars appeared as faint points drifting against a chaotic backdrop, yet their movements carried the clues needed to reveal the invisible object directing the region. Each year, Gez's team recorded their positions with millisecond precision measurements, fine enough to detect shifts as small as a coin moving millimeters from thousands of kilometers away. Over time, the observations revealed clean elliptical orbits. From the shapes and periods of these paths, the central mass could be calculated. One star, S2, proved essential. It completes an orbit in about 16 years, reaching speeds above 7,000 kilometers per second at its closest approach. Only an extremely dense object could produce the gravitational pull required to drive a star to such velocities. NASA later summarized the result in one sentence: the motion of stars near the galactic center provides the clearest evidence of a supermassive black hole. The calculation itself is simple in principle, though demanding in practice. If a star's orbital period and closest distance to the center are known, the mass needed to bind it can be determined. For S2 and similar stars, the values pointed to a compact mass about 4 million times the Sun's. No other object, no star cluster, no collapsed gas cloud could be so dense, so compact, and so powerful while remaining unseen. A supermassive black hole was the only explanation that matched the data. Behind this discovery lay years of refinement. Infrared cameras had to be stabilized against mechanical drift. Atmospheric turbulence blurred the images, requiring adaptive optics systems that reshape mirrors hundreds of times each second to counter distortion. Teams improved detectors, timing systems, and calibrations to ensure that each year's measurements aligned precisely with the last. This was not only a technical challenge, it was a scientific one. You follow the gentle arc of the story as each advance in technology allows astronomers to trace the motions of stars with ever greater subtlety. With every improvement, the paths of those stars become clearer, and the quiet pull guiding them grows unmistakable. By the end of the 1990s, the conclusion rests like a calm truth. At the heart of the Milky Way lies a supermassive black hole. Not a possibility, but a measured reality, working separately with the instruments of the Very Large Telescope. Reinhard Genzel reached the same result, and years later he and Andrea Ghez would share the 2020 Nobel Prize for revealing this hidden. Centered out as you drift deeper into the story, you feel how this finding reshaped more than our view of one galaxy. It offered a broader pattern. If your own galaxy shelters such an object, then countless others may as well. Soon, observations confirmed it. Hubble recorded streams of energetic material stretching across vast spaces, jets so powerful they needed a source of extraordinary strength. A central black hole drawing in matter and converting gravity into radiant energy provided the explanation. Further studies revealed a close relationship between the mass of the galaxy's central black hole and the motion of stars in its bulge, a link now known as the M-sigma relation. It showed that black holes and galaxies evolved together, each influencing the other over cosmic time. NASA described this relationship simply: both grow side by side. This idea reshaped theories of how galaxies form. Black holes were no longer seen as quiet endpoints, but as engines capable of heating gas, sending out winds, and altering when and where stars are born. Even the Milky Way's own black hole, now calm, carries signs of earlier activity. Gamma ray. Structures rising above and below the galactic plane suggest past episodes of intense energy. ESA scientists studying these features note that they may be lingering echoes of earlier infall events. Beneath this discovery lies a longer story of instruments slowly gaining the precision needed to reveal the invisible. Radio arrays, like the Very Large Array, helped mark the position of Sagittarius A*. Infrared cameras uncovered the dense cluster of stars near the core. Adaptive optics sharpened blurred images by sensing the atmosphere's shimmer and correcting for it in real time. Interferometry linked multiple telescopes, creating a resolution far beyond any single mirror. By 2018, a new instrument on the VLT detected delicate relativistic shifts in S2's orbit, subtle changes in wavelength caused by the curvature of spacetime itself. These observations matched Einstein's predictions even in this extreme environment. Then in 2022, the Event Horizon Telescope, a worldwide network of radio telescopes, produced the first image of Sagittarius A*. The glowing ring created by bent light confirmed the mass derived from decades of orbital tracking. NASA called it the first visual proof of the black hole at our galaxy's center. Each piece fits gracefully with the others. The stellar motions, the pinpointed location, the infrared mapping, the relativistic signatures, and finally the image itself. Together they complete the portrait. A supermassive black hole anchors the Milky Way, shaping its structure and history. This insight transformed the search for black holes in distant galaxies. Astronomers now look for characteristic signs: fast stellar orbits, bright accretion regions, long jets, gravitational lensing distortions, and shifting X-ray or radio light. Even when a black hole cannot be seen directly, its influence reveals its presence. The Euclid mission is designed to trace dark matter and galaxy evolution across billions of years. JWST detects early galaxies harboring young black holes. Chandra. An XMM-Newton observe high-energy light from hot gas spiraling inward. Each observatory adds another layer to what you know. Yet among them all, Sagittarius A* remains special. Only 26,000 light-years away. It is close enough for astronomers to follow the motions of surrounding stars with exquisite precision. These stars act as natural test particles, tracing the shape of the gravitational landscape year by year. Behind each measurement lies patient work, nights spent tuning adaptive optics, monitoring atmospheric changes, adjusting mirror segments, checking detector alignments. Every successfully recorded orbit adds a new point to the map of the galactic. Center Andrea Ghez once said that watching these stars is like watching the fabric of space being stretched. Her words describe not only the phenomena itself, but the gentle way knowledge grows slowly, step by step, as the picture sharpens. Tonight, this understanding rests beside you quietly, a discovery that changed astronomy by revealing that galaxies are dynamic structures shaped by immense gravitational engines. And as you hold that realization lightly, another question drifts into view, formed not by starlight, but by motion that refused to follow classical expectations. If the center of the Milky Way hides a compact mass, then why do stars on the outskirts circle the galaxy far faster than visible matter can explain? That calm puzzle leads you forward into the next part of your journey. It is the story of rotation curves, the moment when the speed of distant stars refused to match the glow of the galaxy, hinting at a mass that could not be seen. Astronomers once assumed the outer star should slow down, but Vera Rubin found them moving with surprising speed, far too fast for the visible matter to hold them. Their motion suggested the galaxy should fly apart, yet it did not. This was the first clear sign of a hidden mass felt through gravity, unseen by light. The path to that realization began quietly in the 1960s, before the term dark matter was widely used. At the time, many believed galaxies behaved like enlarged versions of the solar system. Farther from the center, objects should move more slowly because gravity weakens with distance. But Rubin's measurements challenged this view, working at Kitt Peak and Lowell Observatory. She and Kent Ford used a spectrograph sensitive enough to detect tiny shifts in the colors of starlight, Doppler signatures revealing how fast stars moved. Ford's instrument could measure velocities to fractions of a kilometer per second, and this precision made it possible to map the rotation of galaxies layer by layer. Rubin began with the Andromeda galaxy. Its size and brightness made it an ideal target. She studied starlight from regions at different distances from the center, expecting the speeds to drop. Instead, she found the opposite. Stars far from the core moved almost as fast as those near the center. NASA later summarized the result plainly. The edges of galaxies rotate too quickly to be explained by visible matter alone. The rotation curve stayed flat instead of falling, a sign that an unseen form of mass surrounds the galaxies. The idea of invisible mass was not new. Fritz Zwicky had proposed it for galaxy clusters in the 1930s, but Rubin's work provided clear, repeatable measurements across many galaxies. Her results showed that this behavior was not rare. It was universal. Behind these findings was extensive work collecting rotation curves for many spiral galaxies. Each required measuring subtle red shifts and blue shifts along their disks. The assembled data created velocity profiles showing how each star's speed changed with distance. The pattern appeared again and again. The inner regions behaved as expected, while the outer regions retained high speeds rather than slowing. This implied that a galaxy's mass was not concentrated at its center, but extended far beyond its luminous edge. Something unseen added the extra gravitational pull form of matter that did not shine or absorb light. Rubin summed it up with quiet clarity. What you see in a spiral galaxy is not all that is there. It was a simple statement shaped by measurement, not metaphor. If galaxies contained only their visible matter, the outer stars would drift away. Yet they remain bound, held by a presence revealed only through gravity. You arrive at the moment when astronomers felt the ground shift beneath their understanding. A contradiction so persistent that it began guiding them toward a new view of the universe. Galaxies, they realized, must sit inside vast, unseen cocoons of mass. Modern measurements now suggest that this invisible material forms about 85% of all matter that exists. This wasn't born from guesswork or distant theory. It rose from rotation curves, gravitational lensing, the motion of galaxy clusters, and the faint temperature patterns in the cosmic microwave background patterns. Mapped by NASA's WMAP mission and ESA's Planck satellite. Planck's data later showed that the newborn universe demanded far more mass than atoms alone could supply. Those tiny fluctuations, minute temperature shifts, measured in tens of microkelvin, marked places where dark matter shaped the earliest threads of structure, but it was Rubin's careful measurements that shifted everything. Her data offered the clearest evidence that dark matter was not an exotic idea whispered at the edges of physics. It was required. The story of that transformation holds quiet details often left out of textbooks. Rubin spent long nights at the telescope, gathering exposures on photographic plates and later converting them for digital analysis. Each rotation curve was assembled star by star, wavelength by wavelength. With Ford's spectrograph, astronomers measured Doppler shifts with new precision, revealing velocities hidden inside faint starlight. This partnership between patient observation and fine-tuned instruments reshaped the entire study of galactic motion, yet the crisis reached deeper than unexpected speeds. If dark matter surrounds galaxies, then its halo must stretch tens of kiloparsecs from each center. These halos define the gravitational landscape that everything within a galaxy must follow. Stars, gas, drifting dust, even the enormous black holes in the heart of each system respond to their pull. And that meant galaxies could not form from visible matter alone. Dark matter created the wells where gas could collapse, cool, and ignite into stars. Without it, galaxies would not appear as they do. Cosmic simulations, like the Millennium Project, show how dark matter weaves a network of filaments, a cosmic web reaching across billions of light years. Galaxies bloom where these filaments cross. The structure of the universe, its very architecture, relies on this unseen mass. The Euclid mission, built to map dark matter through gravitational lensing, now reports how mass bends passing light, subtly altering the shapes of galaxies in ways that match a cosmos filled with dark halos. These distortions, measured statistically across millions of distant galaxies, reveal mass we cannot observe directly. Even the JWST adds to the picture, capturing early galaxies at redshifts greater than 10 objects, brighter and earlier than expected. Such ancient systems required dense dark matter halos to gather so rapidly. The rotation curve crises opened a larger scientific mystery. If dark matter dominates cosmic structure, what substance is it made of? Physicists proposed many candidates. WIMP's heavy particles that barely interact with ordinary matter. Ixion's extremely light particles emerging from quantum theories. Sterile neutrinos, ghost-like cousins of the neutrinos we know. Primordial black holes formed in the universe's first moments. Yet detectors continue to find nothing. Experiments like LUX, XENON1T, and LZ wait for rare collisions between dark matter and atomic nuclei. These instruments sit deep underground, protected from cosmic radiation, watching for faint flashes or tiny ionization signals inside chambers of ultra-pure xenon. But no confirmed interactions have appeared. NASA summarizes the puzzle simply. Dark matter shapes most of the universe's mass, and still we do not know its identity. And so you return to Rubin's quiet, implied question. How can something so influential refuse to show itself? The tension revealed by galaxy rotation curves remains. Dark matter holds galaxies together, guides stellar orbits, seeds the cosmic web, and directs clusters across space. Asterisk, yet no telescope has seen it, and no detector has caught it. What we do see are its traces, stars moving faster than visible. Mass can explain, lensing stronger than expected, galaxies more stable than their luminous material allows, cosmic patterns unusually even, structures appearing too early. These clues leave little room for alternatives. Still, some research explore modified gravity, asking whether the laws themselves shift in the realm of very low acceleration. Models like Mont and Teves try to match rotation curves without invoking unseen mass. Yet they struggle to fit the full tapestry of cosmological evidence, especially the detailed patterns in the microwave background. The rotation curve crises continues to inspire new missions. Euclid seeks to map billions of galaxies to trace dark matter's spread. The Roman Space Telescope will examine cosmic expansion and lensing with remarkable accuracy. The Vera C. Rubin Observatory will scan the sky again and again, searching for subtle signatures in galaxy motion. All of it leads back to Rubin's original insight of the moment. She traced stellar velocities and uncovered motion that visible matter alone could not explain. Her discovery reshaped cosmology, reshaped physics, and reshaped our sense of what the universe contains. It reframed the very question of what reality is made of. Tonight, the rotation curves continue to whisper their unanswered truth. They remind you that the universe holds more than light can reveal. And as you settle into this point in the journey, another puzzle drifts gently into view, a puzzle woven not from the stars we see, but from decades of searching for something that refuses to be captured. If an unseen substance binds galaxies, why has every attempt to reveal it led only to deeper uncertainty? That quiet uncertainty ushers you toward part 7. Why did dark matter become a gallery of exotic possibilities that no one can confirm? Astronomers could measure its gravitational pull with beautiful precision, yet every effort to find the substance itself came up empty, pushing researchers into a labyrinth of theories stranger than anything expected from ordinary physics. Ideas ranged from invisible compact objects drifting through the Milky Way to particles so light that detectors pass right through them. Each path opened new questions rather than answers. The earliest suspects were not particles at all. In the 1980s, some scientists proposed MATIS massive, astrophysical compact halo objects. These included faint stars, brown dwarfs, wandering planets, and black holes too small to detect through normal imaging. If the Milky Way's halo were crowded with such bodies, their combined gravity might explain Rubin's rotation curves. To examine this idea, astronomers turned to a prediction of relativity, gravitational lensing, when a compact object drifts in front of a distant star. It bends the starlight and causes a gentle, temporary brightening. Surveys like Macho and Ojali monitored millions of stars, tracking changes of only a few percent signals that demanded careful calibration and patience. The results became unmistakable. MACHOs exist, but in quantities far too small. NASA summarized the outcome simply: these compact bodies cannot account for most of dark matter. And so the mystery remained. If dark matter could not be made of faint stars or drifting planets, the next trail led into particle physics to quiet. World of quantum fields, hidden symmetries, and interactions that reach beyond the standard model. One of the strongest candidates became the WIMP, the weakly interacting massive particle. These particles arise naturally in supersymmetry, a theory proposing that every familiar particle has a heavier companion. If WIMPs formed in the early universe, they would be stable, plentiful, and interact only through gravity and the weak nuclear force. To search for them, physicists built deep underground observatories, protected from the rain of cosmic rays. They filled detectors with ultra-pure materials, instruments sensitive enough to catch the faintest glimmer of light that might appear when a WIMP strikes an atomic nucleus. Experiments like Xenon 1T in Italy, the Lux detector in South Dakota, and the LZ experiment hidden beneath the Black Hills each monitored billions of atoms, waiting for a single collision. But the detectors remained still. Year after year, no clear signal arrived. Background noise dropped, purity improved, sensitivity sharpened, and still the results stayed empty. The LZ collaboration eventually reported that no evidence of dark matter interactions appeared in their data. This silence did not rule out WIMPs entirely, but it pushed theorists to look again at their expectations. As WIMP searches continued, another strange possibility grew more promising: the axion, originally introduced to solve a puzzle in quantum chromodynamics. Axions are incredibly light particles that might interact faintly with electromagnetic fields. If they exist, they could form the dark matter that surrounds galaxies. Axion detectors rely on strong magnetic fields and sensitive radio receivers to search for tiny signals produced when axions convert into photons. The ADMX experiment in Washington cooled its instruments to near absolute zero, trying to quiet every source of noise so the weakest whisper of an interaction could be heard. Researchers described the axion search as listening for a signal that hovers just above silence. ADMX achieved impressive sensitivity, yet no definitive detection has appeared. Scientists continue scanning new axion masses and refining their instruments. Another idea: resurfaced primordial black holes. These would have formed within the first seconds after the Big Bang, when small density fluctuations could have collapsed into black holes far smaller than asteroids. Some perhaps no bigger than atoms, yet carrying immense mass. Such objects would remain invisible unless they passed in front of stars or affected their surroundings gravitationally. Interest rose again after LIGO detected gravitational waves in 2015. Some theorists wondered whether the merging black holes LIGO observed might be primordial. If so, they could make up a portion of dark matter. But surveys searching for microlensing events once again showed that primordial black holes cannot explain all the missing mass. Only certain mass ranges remain possible. This expanding list of suspects machos, WIMPs, axions, primordial black holes reveals a deeper pattern. With every new measurement, dark matter seems to slip further from direct detection. The mystery does not come from poor data, but from the nature of dark matter itself. The gravitational clues are overwhelming. Galaxy rotation curves stay flat. Gravitational lensing shows mass in places where no light shines. Galaxy clusters move with speeds that visible matter cannot account for. The cosmic microwave background reveals a universe dominated by non-atomic matter. The Planck mission measured these patterns with remarkable precision. Tiny fluctuations in the microwave background, only tens of microkelvin encode, the early balance between dark matter and normal matter, and these patterns cannot exist without a large dark component. Simulations of the cosmic web reinforce this conclusion. Dark matter must be present for galaxy clusters to form as rapidly as they did. Without it, the early universe would not have had enough gravitational strength to build large-scale structures. Yet despite its influence, dark matter continues to evade detection. This paradox shapes nearly every modern cosmology mission. The Vera C. Rubin Observatory will map billions of galaxies to detect minute distortions caused by gravitational lensing. Euclid will chart how dark matter has flowed through cosmic time. JWST reveals early galaxies that needed dense halos to assemble so quickly. The Roman Space Telescope will measure lensing and expansion with unmatched precision. Each mission narrows the possibilities, searching for what dark matter is or what it cannot be. Meanwhile, other candidates enter the discussion. Sterile neutrinos, particles that interact even less than ordinary neutrinos, might decay into faint X-ray lines, detectable by observatories like XM or Chandra. A puzzling 3.5 keV emission seen in some galaxy clusters sparked debate, though its origin remains unclear. Some theories explore entire hidden sectors particles that interact through forces absent from the standard model. These ideas introduce dark photons, dark forces, even dark atoms, all meant to explain gaps between observations and current physics. But none have been confirmed. Asterisk, even within astrophysics, the puzzle deepens. Galaxy cores rotate more slowly than expected. Dwarf galaxies show massed patterns that resist simple halo predictions. Some galaxies appear nearly free of dark matter at all. Each contradiction forces scientists to refine their models and question old assumptions. Through it all, major space agencies maintain the same quiet statement. NASA notes that most of the universe's mass remains invisible and undetected. ESA echoes that its nature is still unknown. The search balances certainty and uncertainty. The gravitational pull is clear. The candidates are many. The instruments are precise, but the particle itself has yet to appear. Behind this challenge lies decades of human effort. Physicists construct detectors deep underground. Engineers cool vast chambers of liquid xenon to nearly -100 degrees Celsius. Researchers sift through immense datasets, hoping for a single, unexpected trace. Each empty result does not end the search, it sharpens it. Tonight, the dark matter story feels like a list of suspects in a case where every clue points somewhere new. The candidates keep multiplying, yet the mass remains silent. And as you hold this quiet puzzle, another question drifts gently into focus one. Shaped by the uncertainty surrounding these invisible particles, if the force stretching the universe is even stronger than the pull of dark matter, what early observation revealed that the cosmos is accelerating instead of slowing? That unanswered thread guides you softly into part 8. Why was the 1998 discovery of dark energy the most astonishing moment in modern science? Astronomers fully expected the universe to be decelerating, but in 1998, two independent teams uncovered the opposite. The expansion was speeding up, driven by something no one had predicted, a force stronger than gravity itself. This single finding overturned long-held expectations and revealed that about 70% of the universe consists of something entirely unknown. NASA summarized it with quiet clarity. The expansion of the universe is accelerating. To understand why this result shook cosmology so deeply, you'll follow the details of how it was found, why it defied every prediction, and how the data forced scientists to revisit an idea Einstein once set aside: the cosmological constant. The story begins with Type Ia supernova, exploding stars that act as exceptionally precise distance markers. These events occur when a white dwarf, the compact remnant of a sun-like star, gathers mass until it reaches a critical threshold and undergoes a thermonuclear explosion. Because they ignite at nearly the same mass, they reach nearly the same brightness. Astronomers use this consistency to determine their distance. If a Type Ia supernova appears dimmer than expected, it must be farther away. By comparing that distance with the galaxy's redshift, the stretch of its light due to expansion, astronomers reconstruct the universe's expansion history. By the mid-1990s, two major groups were gathering these measurements: the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their goal seemed straightforward: measure whether the universe was slowing down under gravity's pull. The logic was simple: matter creates gravity. Gravity should slow expansion. Everything pointed toward one outcome. But when Rees analyzed the distant supernova in 1998, the numbers quietly resisted. The supernova were too dim, farther than expected. This meant the universe had expanded more than models predicted. The only conclusion was that the expansion was not slowing at all. It was accelerating. You feel the disbelief even now, carried in the quiet words of those who first saw it. Adam Rees later admitted, almost stunned, "We found something completely unexpected." The teams checked everything twice, then again. They reviewed calibration techniques, atmospheric effects, detector sensitivity, the influence of dust, and every statistical assumption. They re-examined light curves, confirmed identifications, and compared methods. Nothing erased the signal. On January 8, 1998, Rees presented the result to the astronomical community, and the room held its breath. Saul Perlmutter's group reached the same conclusion independently. Soon both teams working from different data and methods arrived at the same extraordinary statement: the universe is not merely expanding, it is speeding up. That single sentence reshaped cosmology. Instead of a slow gravitational braking, space was stretching faster with each passing moment, creating more distance between galaxies over time. Scientists named the cause dark energy influence, inferred only from its effect on expansion, not something you can see or touch. Combined with measurements from the cosmic microwave background and surveys of galaxy clustering, the supernova data pointed to a striking balance. Roughly 70% of the universe's total energy density behaves like this mysterious, repulsive influence. The discovery forced physicists to revisit an idea Einstein once introduced: and later abandoned. The cosmological constant. In 1917, Einstein added a uniform energy term to his equations to allow for a static cosmos, then discarded it when expansion was observed. But in 1998, the cosmological constant returned not as an old error, but as the simplest way to describe steady energy per cubic meter of spaciny, pervasive, and able to drive acceleration. The implications are enormous and calmly precise. If this energy density is constant, expansion will continue forever. Galaxies beyond our local group will slip beyond the cosmic horizon, the maximal distance from which light can ever reach you. In a distant future, only the Milky Way's local neighborhood would remain visible. Everything else would fade beyond reach. Yet what dark energy is remains unknown. Possibilities include a true cosmological constant, a dynamic field called quintessence, novel vacuum energy, or a modification of gravity on the largest scales. None have been confirmed. Beneath the conceptual drama lies careful, exacting work. Type Ia supernova are faint at great distances, and their light curves require meticulous corrections for color, stretch, and dust extinction. Atmospheric effects must be removed. Observations use multiple filters to isolate wavelengths. Redshifts are measured with spectroscopy. Each step carries uncertainties that teams painstakingly reduce. The High-Z Supernova Search Team and the Supernova Cosmology Project combine ground-based imaging with Hubble observations, cross-calibrating against standard stars and matching light curves to theoretical templates. Their agreement left little doubt. Then independent evidence arrived from the cosmic microwave background. In 2003, NASA's WMAP mapped tiny temperature fluctuations in the CMB with new precision. The pattern of acoustic peaks implied a flat cosmic geometry, but matter accounted for only about 30% of the needed density. The remaining 70% matched the amount the supernova required dark energy. Planck refined these measurements in 2013 and 2018, strengthening the conclusion. Dark energy appeared across independent probes, supernova, the CMB, and large-scale structure surveys. The same numbers repeated. These observations relied on instruments of extraordinary sensitivity. WMAP detected temperature variations of only a few tens of microkelvin. Planck pushed resolution to arc minutes with still greater precision. Those tiny ripples encode the early universe's contents, showing when dark energy became dominant. Several billion years after the Big Bang, shifting the cosmos from matter-driven deceleration to acceleration. Today, scientists study whether dark energy evolves, whether its density changes, or whether it interacts with matter. Upcoming missions are designed to probe these questions more deeply. The Roman Space Telescope will chart distant supernova with unprecedented accuracy. Euclid will map cosmic geometry using weak lensing and galaxy clustering. The Vera C. Rubin Observatory will watch the sky repeatedly, tracing how structure grows. Each experiment targets subtle signatures, tiny distortions, shifts in expansion rates, patterns of clustering, hoping to narrow the possibilities. Through all of this, one fact remains simple and measurable. Distant supernova appeared dimmer than expected. Their light curves, redshifts, and brightness all point the same way. The expansion is accelerating. From that quiet conclusion, another question arises at the edge of your thoughts. If the universe is accelerating now, what future awaits it billions and trillions of years hence? The answer unfolds softly in the next part. Why does accelerating expansion point toward a cold, silent fate? Astronomers once expected gravity to slow cosmic growth. Instead, acceleration implies a future often called the Big Freeze. As space expands ever faster, distant galaxies recede beyond the reach of light. This does not break relativity, moves through space faster than light, but space itself stretches, carrying galaxies away. NASA puts it plainly: space can expand faster than light without violating relativity. As expansion accelerates, the observable universe shrinks. Light emitted by distant systems can no longer bridge the swelling gulf. Galaxies vanish from view one by one. Over unimaginable time, cosmic structures separate until only the local group remains, a quiet island in a dark sea. Stars burn out. Black holes slowly evaporate, and the cosmos cools toward a vast, lonely equilibrium. This future is not immediate, but the measurements that revealed it are solid and patient. Your view of the cosmos, gathered through careful surveys, precise instruments, and quiet nights of observation, leads to a subtle yet profound forecast: increasing isolation, a thinning of observable light, and a universe that grows colder and quieter with time. Tonight, you hold that thought gently. The same measurements that overturned old certainties now guide your view forward, asking not whether the universe will continue, but how its story will unfold in the long, slow turning of cosmic time. This matters because it creates what astronomers call a cosmic horizon, the farthest distance from which light can ever reach you. As dark energy drives the universe's accelerated growth, that horizon shrinks relative to distant galaxies. Anything far enough away will eventually drift beyond it. Not because galaxies race through space too quickly, but because the space between you and them expands too swiftly for light to cross. You can even express this in familiar units: kilometers per second, per megaparsec, the same units of the Hubble constant. Asterisk, but the deeper consequence is gentle and human in its simplicity. With every passing year, more galaxies slip beyond reach forever. Astronomers first sensed this future when they observed extremely distant systems whose light was shifted far more than older models predicted. Telescopes like Hubble and JWST revealed galaxies at redshifts above 10. Their light traveling more than 13 billion years to reach you. Yet, as acceleration increases, new galaxies will never enter view at all. ESA scientists describe it clearly. Most galaxies in the universe will eventually become unobservable because accelerated expansion carries them beyond the horizon. This leads to a slow future where the cosmos appears emptier with time to understand. How dramatic this is! Imagine the observable universe today. Across tens of billions of light years, you see galaxies woven into a vast cosmic web. JWST reveals early systems forming when the universe was only a few 100 million years old. Surveys like SDSS and Euclid map sprawling filaments and clusters, stretching across immense distances. But acceleration means this grand structure will thin over the next 10 billion years. Nearly every galaxy outside the local group would drift across the horizon. The Virgo cluster will fade. The Coma cluster will disappear. Even enormous supercluster structures, hundreds of millions of light years across, will slide out of contact. Carl Sagan once reflected on the universe's immense scale. Accelerated expansion ensures that most of that scale will eventually slip away from view. The physics behind this fate lies in the behavior of dark energy. Dark energy produces a type of pressure that pushes space to expand faster with time. Measurements from WMAP Planck, DES, and supernova surveys show that it maintains an almost constant density. As the universe grows, dark energy's influence remains steady, while matter thins out with volume. This guarantees that dark energy becomes increasingly dominant. The consequences follow a predictable timeline. 1 trillion years from now, all galaxies outside the local group will have vanished beyond the horizon. Future astronomers, whatever forms of life may exist, will see only a merged Milky Way Andromeda system and a few small companion galaxies. They will have no evidence that the universe ever extended beyond this small island of stars. NASA researchers describe it plainly. Future observers will see a cosmos that appears static and empty, and the disappearance of galaxies is only the beginning. As expansion continues, the cosmic microwave background, the faint afterglow of the Big Bang, will stretch to wavelengths too long for any detector to perceive. Today, the CMB measures about 2.7 Kelvin. Over trillions of years, that temperature will drop closer to absolute zero. The Planck mission charted the CMB with microkelvin precision, revealing the tiny fluctuations that seeded galaxies. But in the distant future, that ancient signal will fade into undetectable wavelengths, leaving no trace for observers to study. This slow cooling leads toward what physicists call the big freeze or heat death, a state where the universe becomes too cold and to spread out for meaningful interactions. Stars burn out. Gas thins until few new stars can form. Black holes evaporate through Hawking radiation, a process that takes far longer than the current age of the cosmos. The universe grows darker, quieter, and emptier with each passing era. Yet the evidence for this future rests on simple, observable quantities: redshift, luminosity, distance, and expansion rates derived from supernova, baryon, acoustic oscillations, and the CMB all point toward accelerating expansion, leaving little room for alternate outcomes. Behind the stark prediction lies a story built from decades of observation. Astronomers use standard candles, Typia, supernovae, to measure cosmic distances. They use standard rulers patterns in galaxy clustering to trace the universe's geometry. They examine the CMB's temperature map to reconstruct the early cosmos. Every method echoes the same conclusion: acceleration. JWST adds to this picture by measuring galaxies from early epochs, showing structures forming sooner than expected, evidence that supports both dark matter and accelerated expansion. Euclid maps dark matter through gravitational lensing, revealing mass distributions that align with a universe driven by dark energy. Surveys like day trace galaxy clustering over time, matching models of a cosmos that expands ever faster. These measurements sharpen predictions about our future. As expansion accelerates, distances grow faster than photons can travel. Light emitted from many galaxies today will never reach you if those systems cross the horizon. This boundary already affects the most distant objects, and it inches inward, relative to far-off galaxies each billion years. Physically, the horizon marks the distance where recession speed exceeds the speed of light, due solely to expansion. It is not a wall or surface, simply a limit on what information can ever reach you. Future observers will see fewer galaxies than you do now. Later, they will see none at all. Eventually, only local stars will remain, and eventually, even those will fade. Say cosmologists summarize this future with a quiet line. An accelerating universe becomes increasingly empty with time. Behind these observations sits a simple physical relationship. Dark energy's density remains constant. Matter's density falls as the universe expands. Radiation's density drops even faster. The outcome is unavoidable. Tonight, this long cosmic path rests softly before you, not as an abstract idea, but as a patient chain of measurements from telescopes, satellites, detectors, and sky surveys across decades. Together they paint a picture of a universe slowly drifting toward isolation, dimming gently as galaxies slip beyond sight. And as that vision settles, another question approaches quietly at the edge of your thoughts, a question tied to the sharpest mismatch in modern cosmology. If we understand the universe's future so clearly, why don't our measurements of its present expansion agree? That unresolved tension opens the door to part 10. Why the Hubble tension has become the most troubling mismatch in cosmology, and perhaps the gateway to new physics. You drift into a quiet chapter of the cosmos, where two ways of measuring the universe's expansion whisper different answers. One method listens to the cosmic microwave background, the faint afterglow of the beginning, itself charted with astonishing care by Yissa's Planck satellite. From that early light comes a value near 6.7. It seems like a small difference, just a handful of units, yet in a universe shaped by billions of years and distances beyond imagination, that gap opens into something vast. These numbers should agree. They don't. And the measurements are now so sharp, so deeply checked, that neither side can simply be waved away. NASA put it plainly: if both results stand, then something fundamental in our cosmic picture remains unfinished. To understand how this tension emerged, you follow the trail laid down by the late universe approach. Astronomer Adam Rees and the SHOES team turned to the Hubble Space Telescope to refine distances using Cepheid variable stars whose rhythmic brightening and dimming reveal their true luminosity. By comparing that intrinsic brightness to how they appear from Earth, their distances unfold with elegant precision. In those same galaxies, Type Ia supernova extend the measurement far deeper into space. Combine those distances with each galaxy's redshift, the stretching of their light as space expands, and the present-day expansion rate appears. This path relies on direct, carefully gathered light, brightness curves measured across multiple filters, calibrations adjust with patience, spectroscopic redshifts verified again and again. Through all of it, the result stays steady, about 73 kilometers per second per megaSea. The other method gazes much farther back to when the universe was young and hot and filled with ripples of primordial energy. The cosmic microwave background holds these ripples as delicate temperature variations, measured in mere microkelvin. Planck mapped them across the entire sky with extraordinary resolution. The exact pattern depends on what fills the cosmos: matter, dark matter, radiation, dark energy. Feed those ingredients into the standard CDM model, and the universe's expansion rate emerges naturally. Planck's answer is equally firm, around 67, with uncertainties now incredibly small. The odds that this mismatch is just random noise have dwindled. ESA scientists note the tension remains, resisting easy explanations or overlooked errors. And so the possibilities gather. The first, some unnoticed flaw in the measurements. Yet Ki-Fi distances have been retuned, supernova. Samples recurated, Planck's systematics re-examined. After years of scrutiny, the disagreement endures. The second, a weakness in the cosmological model itself. Perhaps some assumption inside CDM needs to be rethought. The early universe could behave in ways the model doesn't yet capture. New forms of energy or subtle interactions might be missing. The third possibility leads to deeper waters, new physics, maybe unfamiliar particle-shaped expansion after the Big Bang. Maybe dark energy shifts over time. Maybe the early cosmos carried extra radiation, sometimes called dark radiation. Maybe gravity itself bends slightly differently across cosmic scales. These aren't ideas for spectacle. They arise because the data leaves no gentler option. As one researcher said, either something is missing in our measurements, or something is missing in the universe. Behind this tension lies an intricate story of observation and craft. The SHOES team relies on long Hubble exposures, quiet detectors, and precise distance anchors, like NGC 4258 and the Large Magellanic Cloud. Every step is grounded in known physics. Meanwhile, Planck's high and low frequency instruments observe the microwave background across multiple wavelengths to separate ancient light from foreground dust and other sources. Each piece of this cosmic puzzle is measured with current. Yet the two answers still diverge. This disagreement echoes across nearly every corner of cosmology. A higher expansion rate would imply a younger universe than the model predicts. A lower rate would suggest the early cosmos evolved differently than expected. Either direction forces a revision of our grand timeline. Large-scale surveys reflect this tension as well. The dark energy survey studies baryon acoustic oscillations, subtle patterns in galaxy clustering that act like a cosmic ruler, and finds hints of mismatch with Planck's predictions. The Vera C. Rubin Observatory will follow billions of galaxies across time, tracing how structures grow. ESA's Euclid mission is mapping dark matter through gravitational lensing. NASA's Roman Space Telescope will measure supernova distances. With unprecedented precision, each mission tightens the uncertainty, or reveals that the mismatch is real. If the tension holds, the implications are profound. Dark energy might not be constant. Gravity might evolve over cosmic epochs. The early universe might contain unknown particles or fields. Dark matter might interact in faint, unmodeled ways. ESA scientists suggest that tension could be a signpost pointing toward new physics. Even now, the James Webb Space Telescope adds new questions by uncovering surprisingly mature galaxies at redshifts beyond 10 bright, massive systems earlier than theory predicted. These findings may hint at changes in how structure formed, indirectly touching the heart of the Hubble tension. Behind every possibility lie decades of careful nights at telescopes, quiet hours calibrating instruments, and generations of scientists building upon each other's work. The tension does not come from a simple oversight. It arises from multiple, independent approaches converging on disagreement. Tonight, this puzzle stands as the central unsolved problem in modern cosmology, marking the edge where our understanding grows thin, and where the next discoveries wait in silence. It shapes the questions we carry forward. What is dark matter made of? Does dark energy truly shift with time? And will the coming decades reveal a deeper theory of the universe? These questions guide every new mission Euclid, Roman Rubin age, crafted to narrow the gap or uncover a deeper truth. And as this chapter of exploration settles into stillness, I'm grateful you shared this gentle journey. If this quiet wander through the cosmos brought you even a moment of rest, your presence here means more than you know. A soft tap on like or subscribe is a small gesture, yet it helps these nighttime voyages continue. I'd truly love to hear where you're listening from and any thoughts or ideas you'd like to share. Your words help guide the stories still waiting to unfold, and with that warmth carried forward, we let the final mystery drift into the quiet space around you, a soft reminder of how much remains to be discovered in the vast, unfolding universe. Sleep peacefully now, and let your dreams move lightly among the stars.